it's freaking good as shit. Okay. So let me switch over to this. There is something I have admittedly not done as good of a job with as I should have, but in my defense, we had a lot of other shit just to get through. So let me kind of do a better job of it at the moment. So when he had, oops. All right. So when you have this equation, let's say, let me just make one up real quick. 4t squared minus 8t cubed. Okay. Use a different color, red. So let's say that's my position function, correct? Instead of saying s prime of t, what could I use instead of this? And to be honest, here's the full-fledged thing here. So I really felt there wasn't a great place to focus on this because I wanted you guys to really understand the basics of differentiation. Unfortunately, when I do that, now I've got to try to like backtrack and get you guys used to this. But I have introduced, here's what it really looks like. This symbol by itself means the derivative of something with respect to t. Sort of like this symbol means the square root of something. I just haven't told you what that something is yet. So then if I put this here, those two are equivalent. Those notations are equivalent. And normally we don't write all that business, we just write, let me get rid of this dude. Go away. There we go. ds dt. The one major advantage of this, and by the way, very obviously, there's a disadvantage. There's a lot more shit there, instead of just putting a prime. So there's an obvious disadvantage. But the obvious advantage is, what is S again?
Position.
The position, which is measured in feet or something, right? So like in that problem, it's feet. So the top here is feet, correct? And this is time, change in time. So that would be in this problem, minutes. So if you use this notation, you'll always know exactly what the hell the units are. Now let's do one more step. What if I want to do the second derivative? That would be d by dt of ds dt. That would be the derivative of the derivative. Is that cool? Or understood? Instead of one. You guys might not want to go that far. And the way this looks, it looks like this. It's got d squared s dt squared. So, on that specific problem with the hand card, George completed, that problem on the test, I love the fact that I put the square in the wrong place. And I threw some of you guys off, and I don't blame you. The units on acceleration, is the s squared here? What's squared on top? And why does it make sense it's squared? Because they took two derivatives. So this is still feet. Is the t squared on the bottom? Shit, yes. So this is per square minute. So it should be feet per square minute, or minute squared. Which sounds weird as shit. What's a square minute, Jeff? Is this like a Picasso clock? What is it? So all this means is it's feet per minute per minute. Acceleration is just changing your velocity over time. So it's the change in feet per minute per minute. Therefore, I get minutes squared. Let me stop for a minute. Yes?
I get the dt squared, but I'm still confused with ds squared.
So it's really a notation choice. Does that look like d times d?
Right.
So isn't that d squared? So it's a notation choice. We know that this means I'm taking a second derivative. But the notation, we allow it to look as if I multiply those.
Gotcha.
Yeah. Okay. If some of you guys go as far as differential equations, you're actually going to see that we utilize that in neat ways. We factor stuff with derivatives and so forth. That's way in the future. I'm never going to bring that up again in this class. Okay. The reason I have got to go back to this notation instead of y prime, I want to talk about dy dx, for example. It's because it's going to factor heavily in the next thing we do. Okay. So coming back to my Etch-a-Sketch. So the point there was, I've got prime notation, I've got what's called d by dt or d by dx notation. I could use either one. They both mean the same thing, but one of them has an obvious advantage in certain situations, in this case, units. If I just look at the units in that notation, units on the top over the units on the bottom, I know the units for the freaking derivative I just did, no question. Don't have to sit there and go, okay. So coming back to my Etch-a-Sketch. Oops, sorry. Okay. If I were to rotate, so I'm currently in the middle. There I am. I'm somewhere in the middle. Let me go a little more in the middle. Okay. If I were to rotate both the x and the y in the same direction at the same rate, can somebody be very specific as to what would happen?
Diagonal.
Oh, we get a diagonal, yes. If I wrote them both, one of them only goes x and x, left and right, and the other one only goes in the y, up and down. So if I rotate both of them at the same rate, I'll get a diagonal. Can you be more specific?
A positive slope.
Sure.
Or a slope. Or, no.
What angle? 45 degrees. Why? Because I'm rotating both at the same rate, correct? So of course it's not going to go up more or left more or right more or whatever. It's going to go at the same rate both. So it's going to end up at a 45-degree angle. Is everybody with me? Really want you guys. What would happen if I rotated? Now I got to remember. It's been so long. Let me think. It's this one. Okay. What if I wrote? So this is my y. This is my x. And this is awesome, Jeff. This is easy to remember because it's alphabetical order. X, y. It's crazy. I don't know if they did it on purpose, but we were telling they did. This is my X button. This is my Y button. What if I rotated this button twice as fast as this one? See, from your perspective, like this, right? Yes. What's going to happen?
We're going to rise faster.
It's steeper.
It's going to rise faster than it's running. So you can say the slope is going to be bigger. You can also say the angle is going to be bigger. You guys kind of with me? Maybe. So if I do it at the same rate, it's like 1 by 1. 45 degree. Now it's going to be 1 by 2. Twice as fast, correct? And then I'm going to do the inverse tangent to get the angle. I don't care about the angle. Okay. So everybody kind of with me. So it's not easy to do this. It's like patting your head and rubbing your tummy, whatever. Let me see if I can do this. If I rotate this one twice as fast, that didn't work.
Yeah, that's impressive.
No, it wasn't, Brandon. I appreciate it. Let me see if I can do this. Okay, I'm going to start to rotate this one. I'm going to rotate this one twice as fast. Okay, at the beginning. Forget about the end. At the beginning, it was going up faster than before, yes? Okay, I appreciate you guys. Give me some Etch-a-Sketch license. I haven't sat down and played with this thing. Tried to make Mona Lisa, and she didn't look good. So, let's formalize this into a problem, because I don't know, right now I have no idea how you guys are feeling. This is my intro to this section, and you're all sitting there going, do I have to buy an Etch-a-Sketch? What about spirograph? Later, maybe that'll help. I know. So, let me formalize this. I appreciate you guys going along with me on this. This is the best kind of physical, immediate example I thought I could give in a classroom setting is the Etch-a-Sketch. And I know it's old, who cares? Let's go get it. So here's my XY. So basically my variables are already given to me because I'm considering this XY plane is the plane of the face of the Etch-a-Sketch, yes? So what we're about to get into, they are word problems because you're going to have to pick variables, you're going to have to set up equations. The equations are not going to be as horrible necessarily as back in algebra, for example, when you had a train leaves Wyoming going northeast, blah, blah, blah. another one's random. How long until they hit each other? So, at some time, I'm going to be, let's say, here. Yes? Okay. Nothing has to be perfectly to scale. Just giving myself a little something to look at. I know it's going to go up faster than it's going to go over. Can somebody tell me, so let's say I'm doing 1 click per second on the X button. Is everybody with me? 1 click per second on the X button. What symbols would I use to equal 1? 1 click per second on the X button. How much is it moving in the X direction per second?
So
it's moving 1 clicks worth per second, correct?
dx over dt.
Dx over dt. So listen to me. First and most foremost thing to do in these problems is identify your variables. What is it that will change over time? Those are variables. In some problems, there might be something that doesn't change. Like maybe a plane is directly over and then it flies directly. The height it is up in the sky from the ground doesn't change then. It's not a variable. You can just make it a number. You guys with it? So I've identified my variables, and do you all agree that those two things for the position of this dot as I move it is what's changing? All right. And then I also say, so what's dy dt then? According to what I said earlier. 2 is twice as fast, yes? Clicks per minute. Whatever it is, clicks per second, that's better. I'm not going. Okay. So now my question is, how quickly is the length of this line changing? So I didn't give you the whole problem, so that's okay. I have to use one more variable, don't I? And what variable do you want to use? We have x, we have y. So that's that. So you use z. So the x is changing, the y is changing, and together they're making the z change. So let me ask you this. I really want this section to make the most sense possible. Because this section normally, where students have some trouble, because I think you have an immediate pushback against anything that looks like a word problem. I don't blame you, because you've had some trauma surrounding that, possibly. I don't know. Plus, the math word problems are dumb as hell. This guy forgot how much money he put in the bank. I wish I had that problem. Who's this person? This woman went and bought 200 cantaloupes and nobody asked her if she's okay? I don't know about that. So the word problems are very counter-intuitive, and they're not very real-worldish. Is there a relationship between all my variables involved?
The dt.
Because what kind of shape do they live in?
Triangle.
Live in a right triangle.
Right triangle.
This is x, this is y. So what's the relationship between the variables themselves?
Oh, x squared plus y squared equals z squared.
Yeah. Sorry, do it again. Oh, okay. Is the angle an identified variable in my problem? Is the angle part of the question? So I'm going to say screw, I don't care what the shit the angle is. Whatever it is constant, but it's not even a part of my problem, because I can set up a problem that would involve the angle. Maybe I'll do that second, so you can see the difference. So you guys, we don't use this kind of language, Jeff, very often, but that is a relationship between all the variables in my problem. And let me do a little bit better there at the end. Holy shit. There we go, okay. Let me say this again. That's a relationship between all the variables involved in my problem. My variables are related. The name of this damn section is related rates. So your first step is just to relate the variables. How do I get a relationship between the rates of change? What do you do? What do you do, calculus students, when you want rates of change? You take a derivative. What am I taking the derivative with respect to? Derivative. I'm taking the derivative with respect to time, because what's letting this change is letting time go by, correct? If I don't let time go by, nothing's changing. So I'm going to take the derivative of everything with respect to time. Does anyone see a t variable in there anywhere? No. In fact, this is the coolest thing about this silly little dude. When I graph something on here, is there a t-axis? No, there's an x-axis and a y-axis, yes? Where's the t? I'm the t.
Your hands move.
I am outside. I'm in a different dimension. All these little things are in here going, oh my goodness. We're moving. All right, you guys kind of with me? I'm sorry. It's been a long day for me. I'm a little silly. Right, so this is kind of cool. The thing that is causing the XY graph to form is not present on the graph. It is an external variable. It depends on how quickly I move the dot and the knob. So t is like an external variable controlling both x, y, and all x, y, and z. So if I said, what is d by dt of t squared? What would that be? 2t. All day long. Why is it not chain rule? Because t is just t on the inside. Who gives a shit? But if I say, what is d by dt of x squared? Is the inside just t? No. I really want you guys with me. Some of you guys look as tired as I am. I'm sorry. So what is d by dt of x squared? Is it just 2x? That's a good start, yes. Because the derivative of x squared is 2x times with respect to dt.
Yeah.
Plus. So what's the derivative of y squared? 2y. Every single thing in your equation must have a chain rule piece because they are all functions of time, just nobody tell me what they were. That's what implicit stuff is, yes? And you're all like, okay, Jeff, not only is this word problems, it's implicit derivative word problems, yes? So much more excited. What's the derivative of z squared?
2z.
2z dz dt. So, there's one last thing I want to show you, and the reason I did not tell you earlier is because this is the easiest thing students make a mistake about. They're going to give you the entire problem all at once. I need you to understand what I'm about to tell you. They're going to tell you, and they're of a problem, yes? I want to know what dz dt, remember that was my question? What dz dt is.
Oh.
But I have to tell you at a certain time. So say at, or let's say when x is 3. From a mathematical standpoint, are you guys all cool with what we just did there? I really want you to understand, when I said x squared plus y squared equals z squared, it's a relationship between the sides. It's a relationship between the variables themselves. When I take a derivative, have I related the rates of change of everything? Yes, that's a relationship between the rates of change.
Plug in.
Yes? Do I know dx dt?
Yeah.
No.
Yeah.
Do I?
It's 1.
I do.
Yeah.
I told you, remember? Do I know dy dt?
Yep.
Yeah.
Yes. No, Jeff, stop. Yes, I know dy dt. Do I want to know dz dt?
Yes.
So it's fine that I don't know it, because it's what I want to know. What else do I need to know to be able to figure that out? Don't I have to know what x is? What y is? And what z is, yes? Okay, let me stop for a
Know
minute.
what x is, right? X is
Yes. The problem will always tell you something along the lines of this. Find the change in volume after 3 minutes. Find the change in height when the radius is 7. You guys they have to give me what I call a snapshot moment. Do you understand if I had an infinite Etch-a-Sketch? It starts to be infinite right at where my dogs are, then it's infinite. And I just kept turning them. Couldn't it go forever? Could I just make this sucker and that's just me, just Jeff? It's like whoever the dude was rolling the boulder up the side of the mountain forever. Sisyphus. Yes, thank you. Okay, here's my so I need to know, I know what x is. How can I figure out what y is? If x is 3, what does y have to be? 6. 6.
Yeah.
You with me?
That's twice
So when x is 3, and again, is x always 3? No, at the instant x is 3, everything stops for a moment. It's a snapshot. Time freezes, yes? When x is 3, y is 6. What else do I need to know? This is the only thing I don't know, so I can solve for it. So what else do I need to know?
That z.
Frickin' z. How do I get z?
Just use that.
No way. Yes, they're right there.
So 3 squared plus x squared is 6 plus 36 is 42.
Wait, 9 plus, you can do it, Jeff. 9 plus 6 is 45. Square root of 45 is 9 times 5, so 3 rad 5. I know you all kept up with my mumbling.
Gotcha.
Does all that sound familiar? Okay. You should be able to do it. They gave you 2 sides of a right triangle. You should be very happy. Then my question is, what's the third side? Okay. So now I've got everything I need. You all agree I can kill the 2's? I can divide both sides by 2. Is that right? I can do better than that. Die. And so x was 3, dx dt was 1. Y was 6, dy dt was 2. Z was, what was it, 3 rad 5? Yes. 3 rad 5. dz dt, I don't know. Could you solve that for dz dt? Hell yeah, Jeff. So I get 15 divided by 3 rad 5, is that cool? Right? 3 times 1 plus 6 times 2 is 15. Divided by 3 rad 5. And then just throw in the old calculator. So you get rad 5, which is like 2 point, I suck at this, 2.13. Somebody tell me how badly I did. 15, you gotta be really careful when you place it in the calculator. Just do square root of 5, because that's what that is. What's the square root of 5? Yeah?
Square the y, the 2y, dy, dt. What happened?
Oh, I divided them all, sorry. Let me put them back, and then we cancel. We divide both sides by 2. Yeah. What is the square root of 5?
2.236.
Oh, not too bad. I can live with that. 2.24 roughly. Clicks per second, whatever it was they said. So again, most of the problems in section 3.9, you're going to set up, you're going to draw a picture for a lot of them. Identify what the variables are. What's the equation that relates all of those? It's not always going to be frickin' Pythagorean theorem. Why was it this? Because I had a right triangle. And I cared about the sides, yes? Set up the equation, take derivatives, right? The very, very first thing you should do really is collect what they tell you in symbols, identify what they ask you in symbols. You then know what to look for. You should have those things in your, when you take the derivative, those should be there, yes?
So do you want us to put the answer in exact form or?
Yeah, for word problems, we kind of want to do decimals. Yeah, because normally, you don't want to say I live about 3 square root of 5 miles away. Yeah. Even if that's true, it's a weird way to put it. So let me give you this, and we're going to do this first problem together. This is perfect because it involves an angle.
An angle?
An angle. I know for some of you, I lost you at word problems. I'm sorry. Come back to me. Come back to me. So can you guys read through that first problem? Does anyone have any questions about any phrases or words in that problem? Specifically, does everyone remember what angle of elevation means? Does anyone remember what angle of elevation? Why did nobody have a question about it?
Well, like you're like looking at a tall thing and it's your angle.
So, yeah, it's always angle of elevation and angle of depression. They are both measured with respect to you looking straight out. So if I look straight out and look up at the top of the wall, yes? You guys with me? I look through an angle. What happens if I get closer to it? What happens is angle? It increases, yes? And this is just at the movie theater if you got there late. Yes? Remember that? I've seen several movies where it's like, I either read what they're saying or I watch the movie. I can't do both.
Or if you're on top of the building looking down.
Yes, if you're on top of the building, you go through an angle of depression to look down at somebody on the street. You guys all with me? So it always starts straight out, and then you measure the angle from there. Yes?
When we're looking at the graph, so I know the change is like how fast the line is going up or to the side through the y and x axis.
Are you talking about this problem or the one we just did?
Just the concept. So we know that like when we drew the graph, we had y and x, right? And we knew that the rates of change on x and y, right? So when we like take a snapshot, is to the y and x axis like the values that we have, they represent how many clicks or clicks per second?
Oh, the x and y values would be the number of clicks.
Just numbers.
So x was 3 clicks and y was 6. The derivative would be change in position divided by change in time. That would be clicks per second or whatever. Yeah. Okay. So real quick, a plane. So we're standing here, and a plane flies overhead. Right? We're in South Park. There's that one place where it just comes out of nowhere. Oh no, it's already been there. And it continues to go. So we kind of track it as it goes. So when it's right overhead, what's the angle of elevation? 90. And then it's going to move, and so what's happening to my angle of elevation? Decreases. Okay, good. So did the problem involve you knowing what I just said? No. Do you understand the problem better, or maybe able to do the math better if you understand what I just said? Yes. Maintains a constant altitude of 3 miles. So it's above us at the same height the whole time. Can you draw this situation, put yourself on the ground, put the plane in the air at some time, some arbitrary time after that? A few seconds after it's gone overhead, can you draw that situation? Try it. You might as well try it because you can't go wrong because I'm not going to look at it unless you show it to me. So a big problem with these problems is going to be drawing the picture. What?
You want to measure it?
Oh. Okay. Where's the angles?
This is nuts.
Oh, okay. Alright, so here I am. Plane flies, it's overhead, so what's this?
3 miles.
So that's 3 miles. So I can put a number there. Why am I able to put a number there? No problem. It's a constant. You can only put a number if it's definitely going to stay the same. Because here, after 10 minutes, I'm not going to use that to calculate anything about the picture I'm drawing right now, because that's my snapshot.
It says miles per hour.
Yes, good.
But it's in minutes.
I love it. So we're going to have to take care of that. So after some time, the plane is now maybe right here, yes? Here's my beautiful plane. This plane is not going to do well. Looks more like a submarine, but don't ask how it got up there.
Potato
it looks like a cat.
Potato air.
Yes, a cat. It's flying the feline skies.
Better than spirit.
We where is the angle of elevation? So what should I draw in? I should draw in my line of sight going straight along the horizon. And then my angle of elevation would be here. What other variable, what other aspect of this drawing I've just done changes over time and I care about it? Let's see if you guys are cool with that. Do you agree that the line from my eyeball to the plane, isn't that going to change over time?
Yes.
If you read through this problem, do I give a shit about that? No. They don't tell me anything about it. They don't ask me anything about it. I'm going to leave it. What do they tell me about, though? Did they tell me how quickly the plane's moving? Oh, so they tell me something about this. So I better give that a freaking variable. So what do you guys want to call this? By the plane, huh? No way. Okay. It's parallel to the x-axis. You can call it P for plane. You can call it whatever. W for why the shit are we doing this? Whatever you want to call it. Do you notice a problem with my angle versus what I've identified? My triangle.
Outside.
My angle is not in my triangle. So one way you can take care of that is to either move the angle to here, because you got transversal and you got parallel lines and all that shit. If you forgot all that shit, just make your triangle go here. What's this? This is 3. And what's this? X. Okay. Let me stop for a minute. Again, the reason this is hard for you guys is because you don't get a lot of practice with this, which makes me cry. I cry a little bit. Mathematical modeling is how math relates to the real world. If I cannot model the real world in a mathematical way, I cannot use the math I've learned to help me understand the world. That's kind of important. So it sucks that you don't get a lot of practice with word problem kind of stuff. Does everything I've said make sense? What do you need to focus on? What's remaining constant? I could put a number there. Is there any part that might change over time? I better put a freaking variable there. Because it changes, it varies. Hey, variable. What part do I not care about? In this case, the diagonal. I don't give a shit about that. That was actually the whole thing in the Etch-a-Sketch problem, but here I don't care. Do you agree? Do I have anything I've left out? Is there any of the variables I forgot to identify? Anything else? Do you worry about that guy's name? That's me. That's us.
300.
Ah, good. Okay. So what's 300? What notation can I give 300? Good. It's how quickly x is changing. Yes. So over time, the plane moving is going to change this length. Does that make sense? So good. So far we have our first 2 steps. First step, identify the variables in the process of drawing the situation. Second step, what are the symbols for what they tell me and the symbols for what they ask me. So dx dt is 300. The last thing you worry about is the snapshot. What is this at a time when this? Yes, sorry.
Earlier you mentioned if 300 miles per hour for 10 minutes.
We're going to take care of that when we get to the snapshot.
Okay.
Yeah, you'll see. It won't be that big a video. What are the units on what they're asking me?
Miles an hour.
No, I'm sorry. I didn't mean units. What's the symbol for what they're asking me? D theta dt. So try again. What would the units be? Radians per minute. What do we always use now? Where's my trig guys at? Bart with me now. So radians, because that's the one that actually is a physical measurement. Yeah. So the question is, what's d theta dt? So what's the relationship I can set up? What relates the variables I've identified in my picture? Do I use Pythagorean theorem? No, because I have a variable for this that I don't care about. So what do I use instead? I probably do what the guy tried to tell me to do earlier.
Tangent.
Yeah, what trig function involves these? Tangent. So I've got tangent theta equals
3 over x.
3 over x. Or x equals 3 over tangent theta. Is that cool?
Yeah.
Or x equals 3 cotangent theta. Is that cool?
How would it?
plus
It doesn't
1
really
over
matter.
10.
I didn't want my over x to be in there. I don't want to deal with that. You guys see what I'm saying? We're going to do implicit anyway. I might as well get my letters in a good spot. And I don't want a letter on the bottom because I don't want to deal with that. All right, let me stop for a minute. Yes?
I need a little question. How did you switch from 3 over tangent to cotangent?
Oh, what's 1 over tangent? Okay. And I did that just to make the derivative easier. It's easier to do cotangent derivative than it is to do 1 over tangent derivative.
Right. Makes sense.
Yes?
Just to clarify, we can't solve for the angle there, right?
I mean, you could, but do you want to do derivative of an inverse cotangent? No, neither do I. And you don't have to. That's the beauty of implicit. You could. I don't want to. Yes?
Those 3 possible.
These are all the same equation. I rewrote it, and then I rewrote it again.
Okay, so.
Yeah, here I divided by tangent, multiply by x, and then here I just made it 3 cotangent. So let me tell you why. If I multiply x up, don't I have a product rule now? You guys with me? If I multiply x up, wouldn't there be a product rule? X times tangent. That would be product rule, correct?
Yeah.
If I divide the tangent away and then make it cotangent, now I don't have product rule, I don't have chain rule, I don't have quotient rule. I just have straight up derivatives. Do you guys understand? This is an extension of simplify the thing you're going to do calculus to, right? For example, like the x times the cube root of x squared times the square root of x. For example, right? Maybe multiply that shit out first, okay? So, what can I do now? Do I have a relationship between all the variables involved in my problem? Yes. So what do I do? Do it again, sorry. Yeah, take the derivative. So what's the derivative of x with respect to t? I mean,
1 times.
I'm going to take the derivative of both sides. So derivative of x with respect to t is dx dt. What's the derivative of cotangent? Cosecant squared theta times
Cotangent, or 3 cotangent.
D theta dt.
d theta
Oh,
dt.
d theta dt.
Okay, I got too much stuff going on here. Stop for a minute. Anytime you wanted to, you could have taken a derivative of this first guy. It would have been a little bit worse than it had to be. You could have taken a derivative after you multiply the x up. You would have used product rule. It would have been worse than it had to be, but it would still work. Yes?
How is 3? Because trying to figure out why would you take the derivative of cosecant only and not 3?
So again, guys, help me out. Okay. What is the derivative of x? I'm sorry, derivative of x with respect to x. But isn't there a 1 in front? So shouldn't you have to do 1 prime x plus 1 x prime? Do you guys agree that we don't have to do that shit? Isn't that insane? Derivative of x is 1 because the 1 will be left that's in front. So what's the derivative? So this is crazy. Derivative of x is 1. So what's the derivative of 2x? Freaking 2. I don't do 2 prime x plus 2x prime because the number comes for the ride. If I did a product rule with a constant, when I take the derivative of the constant, that part goes to 0. So why even do it? So we've tried to build into the way we do derivatives, the numbers just come for the ride. So if I did do it, it would be 2 prime x plus 2x prime. Some of you guys do that, but then you get this. I don't know, you get this. Or something. Shouldn't this be 0?
0 plus 2.
Yeah. So don't do that. So when you see a problem like this, the 3 just comes for the ride. I just wrote the 3. It just comes for the ride. What's the derivative of cotangent? Negative cosecant squared. Yes?
So, where your finger was at, with a 3 to cosecant squared theta, so when you moved it down, it's to a negative 3.
Yeah, what's 3 times negative cosecant squared?
Oh, I didn't see the negative there, sorry.
I'm sorry, yeah. Because derivative of cos stuff is always negative. Yes?
Can we just skip right into USDT and just throw the 300 there so we can see because we know that? Or would you take points off like all of the skip steps? Let's take the 5 and roll that and do
You need to get it all the way written out so you put the right stuff in the right place. So I understand in this problem there's not a lot going on. So I understand you could put a 300 there and I probably wouldn't bat too much of an eye, right? But there's going to be a little bit more going on than some of these. Yeah.
So, I'm just trying to get this straight for myself because we're taking the derivative of an x and technically an inside function, which is theta. X would turn into dx over dt, and then you chain rule the theta.
Yep.
The d theta over dt.
So tell me this, why do I have to ever use chain rule? What is that I keep saying? If I'm taking derivative with respect to x, I have to use chain rule if the inside is more than just x. So what am I taking the derivative with respect to in related rates? T. And every variable is a function of time. That's why we gave them variable names, correct? So they're all functions of time somehow. So they're all chain rule automatically. So yes. So the derivative of cotangent of something is negative cosecant squared something times the derivative of that something. So that's why it's times d theta dt at the end.
Yeah.
Good.
I just thought of it as like chain rule.
Yeah, no, totally.
Yeah.
That's all implicit is chain rule. Because the inside function is more than just a function of x, or in this case, a function of t. Okay. It's a function of t instead of just being t. Yes. Okay. Yes.
I don't really understand why it's d theta.
What's the inside function of cotangent? Theta. And do you agree that theta is changing over time? So do you agree theta is a function of time? Yes. It's just like me saying what's the derivative of the square root of sine x? Well, the inside function is sine x. So don't have to use chain rule for it. So this is the derivative of cotangent stuff. So I have to multiply by the derivative of that stuff. So let me do this. What if I had this equation? Yes? And I want to take the derivative with respect to time. How would you do it? T. What's the outside function?
Negative cosecant squared.
So that's negative cosecant squared of stuff times
Times derivative of
8t. And what is this? This is the derivative of 4t squared with respect to time, yes? That's just chain rule, correct? So what if I said, okay, this time, I'm not going to tell you what this is. It could be 8t cubed. It could be sine of t. I'm just going to tell you it's theta and that. I don't tell you explicitly what is a function of t as. Is it the square root of t? Is it sine t? I don't know what the shit that is. So when I take the d by dt of it, negative cosecant squared stuff times derivative of stuff, as always. You guys are getting really good about seeing this, and I really appreciate that. I just need you to take the next step and realize this is exactly the same thing. If theta was 4t squared, wouldn't d theta dt be this? So if I didn't have this here, I wouldn't be right, because then I wouldn't have gotten this there. That's all it is. Okay. Yes?
So basically, the d theta over dt is just equals to d prime, or not?
It's like theta prime. Yeah. Sorry.
You put data prime instead of that.
I mean, you could, but I need you to start understanding that the prime notation is not generally good enough. What do you guys, when you see y prime, what do you expect that to be with respect to x? Correct? Now you're seeing if I let prime be any derivative I take, I'm losing some really important information. Is there any t variable in the shit we did on the other side? No. So if I put primes, I'm completely hiding what that's in reference to. It's in reference to x. Well, no, we put a dx. You put an x prime. So what is that? So we have to be more explicit. Plus, units are going to be involved in this thing. And what I say is the most important advantage of this notation: units.
So t on the bottom is just in respect to t.
In respect to time.
Yeah.
Yeah, in respect to t.
Alright.
I
So
like it.
derivative of theta, the derivative of time over the derivative of time.
How much the theta changes as the time changes.
Okay.
That's literally what the d theta dt means. Yeah.
I just have a observation. Is
Yeah.
dx over dt divided by d theta over dt?
Wait, do it again. Sorry.
Is dx over dt divided by d theta over dt? Can we simplify that or no?
Oh. Yeah. So, okay. Do I want to have this discussion right now in the middle of this? No. I'll come back to that. Okay. So guys, help me out. Do we know anything in here?
Yep. dx dt.
Yes, we know dx dt. What's dx dt?
300.
Yeah, 300
miles per hour.
Now Mercedes back there saying, I'm already there, man. Do I know, and what is it that we want to know? What is it that it's asking for?
D theta over dt.
D theta dt. So that's okay that I don't know this. I don't want to know this. I want to be able to solve for it. So what other thing do I need to know? Yeah, you could think that you need to know theta, but what you really need to know is cosecant theta. So let me see you guys. Let me see. I'm going to let you think about this for a moment. Don't say anything out loud. There's something I wrote, almost the first thing I wrote. Not the first thing I drew, but almost the first thing I wrote. It's the first equation I wrote. You could draw a triangle, you could figure out what cosecant is. You cannot figure out what theta is. Now here's the other thing, let me help you out. Oh, let me even make this better for you because I'm just remembering that we have more information. Didn't it say after 10 minutes? Okay, so I can actually figure out what this is, yes? I can put a number here, yes? What do I have to be careful about? I know how fast I'm going in miles per hour, like you guys said earlier. Well, 10 minutes is how much of an hour?
6.
Yeah, don't I need 6 groups of 10 minutes to make a full hour? So 10 minutes is 1/6 of an hour. So how fast are we going? Or how fast is the plane going? Yeah, 300 miles an hour for 1/6 of an hour. So how far has it gone?
50 miles an hour.
It's 50 miles, right? 300 miles per hour times 1/6 of a mile. I'm sorry, 1/6 of an hour. Let me write this down. Yeah, snapshot time right here. 300 miles an hour times 1/6 of an hour would give me 50 miles.
50 miles per hour.
No,
No.
this is miles per hour, and this is hours, so the hours cancel.
So miles per minute. Just
Miles.
Just miles.
Yes. It gives me a distance I've gone, right? If I know how fast someone's going and I let some time go by, I know how far it's gone. Oh, yeah.
If you get a final answer that has different units than what you would have wanted, would that
What do you mean?
let's say we instead change the rate into 5 miles per minute instead of making the 10 minutes into 1/6 of an hour.
Oh, I see what you're talking about.
And then we had the final answer in radians per minute.
Oh, I see what you mean.
Change the thing.
Sure. You could change as long as your time units are the same. Yeah. Then you would make your t minutes instead of hours.
Yeah.
I'd be fine with that. Yeah.
Thank you.
Okay. So now we know that x is 50. Yes. So the snapshot time x is 50. Now look what comes into play. I want to know the cosecant, don't I? Because we have the answer staring us in the face, the way to get the answer, but I just need to know what cosecant theta is. What am I missing to figure out what cosecant theta is?
Figure out what.
Do I have a right triangle?
Yeah.
Do I know the ratio the cosecant wants from me?
Yeah.
So what side am I missing? Hypotenuse. And wouldn't that just be 50 squared plus 9? 2509? So what is the cosecant then? In fact, let's be even better. What's the cosecant squared? I don't know if you guys... First off, what's the cosecant?
1 over something, so
Sure. Hypotenuse over y. So 25, square root of 2509 over 3. Yes? Okay. So what's cosecant squared?
2509.
Oh, yeah.
2509 divided by
Oh, square
9. There it is.
9.
Is everybody cool with the rad 2509 divided by 3? Sine is y over hypotenuse. So cosecant is hypotenuse over y. Right? Is this reciprocal of sine? Okay. So cosecant must be hypotenuse divided by the y side. Square it, I get the square root dies, and 3 squared is 9. And now I just got to plug that in. So now I know cosecant squared is 2509 divided by 9, and now I can finally solve for d theta dt. Man, I'm the king of figuring out how much room these things need. So let's see. Oh, Jesus, Jeff, you're going to try this in your head. Negative 100, negative 900 divided by that. Who knows what that is? I don't think anybody can know what that is. Negative 0.36. Negative 0.362.
0.35.
Damn it! I went the wrong way. Shit. I suck. I'm sorry, guys. I'll retire. What's the units on this thing? Radians per hours. So if you did it your way, it would be 6 times as big, right? Because you do per minute. 60 times as big, yeah.
60 times less.
Yes, less. Thank you. So, the most important thing to get from any problem we do together is what was the motivation behind each step? For you guys, the motivation is probably, let me just get through this shit as quick as I can.
And like find the give-ins and then
You will almost always draw a picture.
draw a picture.
In fact, off the top of my head, I can't think of a problem I signed where you don't want to draw a picture, but maybe that's not right. I can't remember. You will almost always draw a picture. You will then assign variables to anything that's changing in the picture over time. So it's good to imagine the damn thing, the plane is up there, now it goes over there. So obviously this length is changing, obviously the angle is changing. You start to see what variables you need and which ones change over time. Once you set up your picture and you get your equation, you can simplify your equation if you want to. You can attack it immediately with calculus, right? One thing I missed was you want to capture what I tell you in symbols and what I ask you in symbols. Just so you can make sure if the what I ask you doesn't show up in your equation after you take a derivative, you're screwed. You obviously did something wrong. If you don't have a d theta dt, there's no way you can figure out what it is. Okay. Sure. I can even do something better. Ooh, technology. Now, on number 2. Yes, go ahead.
For the answer, I get the number. Is that units?
Sorry?
Negative 0.359.
Yes?
The end bit.
Radians per hour. Yeah. And real quick, why does it make sense it was negative? Remind me, my angle of elevation starts off at 90, and as it flies, my angle of elevation gets Smaller. So the fact that it's negative over time makes sense. It should be decreasing over time, yes? So get over the algebra knee-jerk reaction and negative numbers being bad. Don't throw them out. You need this to be negative. Okay. So just to illustrate the counterexample to what I just said earlier, do you see number 2? Why is number 2 easier? Can you even tell me why number 2 is easier immediately?
You already got the formula.
I already got a formula. I don't have to make it. The hardest part about this problem, let me see if you guys agree. There were some other tricky parts, but the hardest part was just getting to the formula. Identifying the variable, everything that you had to do to get to the formula. Well, look at number 2. I give it to you. Yes? You're welcome. So, try 2A. Use symbols for what they tell you, provide symbols for what they ask you, and then go for it. Do you plug 24 in right now?
No.
No, that's the snapshot. You let the radius changes. You gotta let it change, and then you plug it in after you take a derivative. If you plug it in right now, derivative is gonna be 0 for everything in the universe, right? Then we're all still living in cases. But somehow we have iPads. Yes.
I have a question on the first one. So on the very bottom and very end, I might be putting in my calculator wrong, I'm guessing, because I'm thinking the negative 3, I'll multiply it by 5 over 9.
Sure.
By 9, then divide 300 into that.
No, divide 300 by that. You gotta divide by this, you get that by itself. Yeah. Okay. So what can you guys do immediately? What are you guys doing? Are you drawing a balloon? I don't blame you because I made a big deal out of drawing. But this is a very specific example where you really don't.
dr dt equals 4.
Good. dr dt.
And that's giving us the
4
force.
centimeter cube per minute.
I want to know, yes?
Well, I thought you were giving me the rate of which that at that time.
No, probably
No.
rate of change.
No. What rate do I tell you?
dv over dt.
dv over dt. I tell you what that is, don't I?
Yeah.
4 cubic centimeters per minute. How do you know that's a volume? Because it's cubic centimeters.
Cubic
Yeah.
centimeters, yeah.
You're okay, Mercedes. Don't worry. You look about as tired as I am, so it's understandable. So look for the units. That will help you. So if gas is escaping, the volume is decreasing. Obviously, if the volume is decreasing, the radius must also be decreasing. By the way, I've written one thing incorrectly. No, you're like, really? I didn't do it on purpose, I'm sorry. Gas is escaping,
Yes.
so the volume of this should be decreasing, so it should be negative. All right, is everybody cool with what's happened in this problem so far? This step is going to be on every problem. It normally happens, it's either the very first thing you do or immediately after you draw your picture and so forth. Identifying in symbols what they tell you, what they ask you. I've already given you the formula. That's the worst part of it, so I already gave it to you. So what can you do with that formula?
Derivative.
I'll tell you what you do with it, Jeff. Hey, yeah, take a derivative.
8 pi r.
Almost.
No, wait, 8 pi squared times.
4 pi r squared times dr.
Yes.
Yeah, that's
So
derivative.
dv dt, right, equals, got to do the both sides. The 3 comes down, pass it around, you get a 4 pi
Squared.
r squared times
The
No.
R.
dr dt.
dr dt. Derivative of the inside. Radius is a function of time. If radius is changing over time, it is a function of time. So what's inside of my cube? A function of time. So I have to do chain rule. Just like if I had y cubed, it would be 3y squared times y prime, because the inside is a function of x. To take it through the chain rule. Do I have everything I need here?
Yeah.
What's dv dt?
4. Negative 4.
Negative 4. Do I know r?
24.
24. And I don't know dRdt, which is fine, because that's what I'm trying to figure out. Yes, sir.
So when we're writing like we're putting the negative, even though the question implies that it's shrinking, we still include the sign.
Yeah. In fact, since the question implies it's shrinking, or just states it's shrinking, I must put in a negative sign. That's the right way to look at it. It's getting smaller over time, therefore it must be negative.
Yeah.
If it was positive, it'd be getting bigger over time. Yeah. And now it's just a matter of plugging all that shit in your calculator. Just divide by all that business. You want to try to do it in your head, Jeff? No. Sort of. 576 times pi. No, I don't. Is that okay?
But we put it in scientific notation.
Huh?
Don't we leave it in scientific notation?
Oh, sure. Yes. So it'll be negative, the 4's cancel, is that cool? It's going to be negative 1 over, I just had this a second. Is it 576? What is that? No, sorry. That's way too small. 400. No, that's right. 576? 24 squared. Thank you so much. Everybody's looking at me like I'm insane, which is true, but not for that reason. And then just throw that in the old calculator, right? Don't put in your calculator negative 1 divided by 576 times pi, because the pi is being divided. So it'll be negative 1 divided by 576 divided by pi. I don't know what you'll get, yes.
So did you get negative 4, right?
That's what they told us. Right from the beginning. They told us gas is escaping at a rate of 4 cubic centimeters per minute. So I know dV/dt is negative 4.
So that cube, centimeter cube, 4 is the.
Say again, sorry?
The centimeter cube
What do you mean it doesn't matter?
That's our units.
Oh, yeah, the units I don't normally throw in there. So, real quick, dV/dt is going to be cubic centimeters per minute, correct? All right. R is in centimeters. R squared would be centimeters squared, correct? dr is centimeters. Isn't it centimeters cubed per minute? Doesn't it match up with centimeters cubed per minute? What I just did, if you were paying attention, I understand some of you guys are doing this kind of thing. I understand. Trust me. I just did what's called unit analysis to make sure one side's units better equal the other side's units. So let me do it again. Centimeters cubed, cubic centimeters per minute. Square centimeters times centimeters is cubic centimeters per minute. Unit analysis. That's a surface level thing you can do just to make sure the equation makes physical sense, right? That'll help you remember if you left dr/dt off, your units don't match for shit. So then you immediately know, oh, I left something off. What is this, by the way? Has anybody done that for me? Like, I'm not doing anything for you.
Negative.
183.
Sorry? Negative?
183.
No.
I've got negative.
Should be really, really tiny. 1 divided by 576 pi.
I've got negative 5.53 times 10 to the negative 4.
Sure. Units. What are the units?
Centimeters per minute.
Yes. Centimeters per minute. I was lagging in real life there for a second. Very tiny change. Poor little thing. Okay, you guys are reacting appropriately. So this one was nice. This one, I probably should have put this one first because that first one was a little bit of a bear, but I just like to start with the first one because it has all the parts you're going to have to look for. This one was much nicer because, again, they gave us the formula. So I can just basically do the derivative of that right away, and then I can go, what do they tell me? What do they want to know? And plug the stuff in. Yes?
What happened here? Oh,
Okay. That's up there. Okay.
Okay.
Let's do part B and then we'll take a break. See, part B is the same as part A, correct? What is it they're asking me for in symbols?
ds over dt.
D big SS over dt. And they tell me the radius is 24 centimeters, and I still know, what do I know now about, well, let's see, okay, I'm not going to tell you, oh shit, go ahead and take the derivative. I'm not going to tell you a damn thing. And you're all like, yeah, it sounds like you. Sounds like something you would do, Jeff. So when you get with the derivative, you get 8 pi r dr dt. 8 times pi, I know r is 24, and dr dt I know. I'm going to use this because I'm weird. But you see why I'm going to use that? Isn't that the same thing? This is a better form. Why? Because the pi cancels, for example. And I'm not rounding, is the other thing. Where did we get this from? Where did we get this from? By plugging this in the calculator, yeah? So these are the same thing. This is exact. This is an approximation. It's an abomination. It's an approximation to this. Why? How do I know it's approximation? Because the decimals go forever. I would put a lot of money down on that fact. Now, could you have plugged this damn thing in here and would I have cared that much? No, I would not have. Yes, you could. No, I would not care. Right? That'd be fine. But it's better to use the non-rounded number. Now, in your calculator, just do 8 times 24 divided by 576. It's not a point there. I don't know why what that thing is. Almost 576. Nice. 4 times 24 squared. So it'll be 4 times 24. It'll be 2 over 24. It'll be negative 112, I think, which is negative point. Oh, 879?
Negative 1/3.
Negative 1/3?
Yeah.
What did I lose? I lost something. It doesn't matter. All right, I'm gonna let it go. Is it negative 1/3?
Yeah.
Okay, I'm happy. Okay. Negative 1/3 what?
Centimeters squared.
Good. DS, surface area, is square centimeters per minute.
You can leave it in fraction.
Huh?
You can leave it in fraction.
Yeah, when it's 1/3, you're fine. If you said you lived 1/3 of a mile away, I'm not going to look at you like you're insane. But if you said you lived square root of 11 divided by 7 miles away, I'm going to look at you like you're insane. Let's take a break. That's plenty. Go talk about how much I hate this and then come back at 10 after. I'm not going to keep us all the way. I'll let us out a little early. So come back at 10 after.
Do you know what face down is? Oh, it's the red jumpsuit apparatus.
Oh! Well, that changes everything. No, I still don't know though.
Still know.
But I like this. I like the name. It's good. I like that.
I only know one song from that.
It's like Toad the Red Sprocket.
Yeah. I'm so tired.
All right, guys, we got one more problem, but it's got many, many parts to it.
Ooh-wee.
Too bad.
Ooh-wee. Ooh-wee.
All right, guys. What I'm trying to do with these examples is to show you some common themes you might see in some of the problems you're going to have to do in the homework. So you'll get a couple like number 2. More of them will be like number 1. And then you'll definitely get some like number 3. Number 3 has an idea in it that will show up in a few problems. And it's called similar triangles. When I say similar triangles, does anyone know what that reference is? Proportions. I love proportions. Yeah. Like 3, 4, 5 is similar to 6, 8, 10. It's just twice as big. So all the sides are in proportion to each other.
Wait, can I ask a quick question?
Yeah.
Was there a way to find DRDT if we didn't do part A first?
If you didn't do,
Part A first, step number 2? Or would that just have to continue variable?
Well, because it requires you to have.
if I only knew what part B gives me, I wouldn't have enough information.
Okay, that's all I need.
Yeah. Because in this equation, I have 2 unknowns.
Yeah.
And I've got to know one of them, yeah. Okay. One thing that number 2 does for you real quick is that sometimes what you find in one part might get used in another part. Keep that in mind. I don't know, just in general. For a problem I might give you on a test or something, I don't know. All right, so read through this. Water is draining from a conical tank. Oh, shit. And by the way, I will give you, I can't remember if I did this on the back. I'll give you the formula for the volume of a cone. I'm not going to assume you know. It's really stupid cool, though. Real quick. Just deal with me. I'm going to give you the formula, but I just want to talk about this real quick. There's a category of shapes called pyramids. And a pyramid is not what comes to mind necessarily when you think of a pyramid. So I can make a pyramid. Your classical pyramid has a rectangular base, and then it comes to a point from every corner. Yes? Now that's a shitty pyramid, but for me, it's pretty good. A cone is the most basic pyramid. Because every corner of the circle, meaning every point on the circle, goes to a single point up above it. So it matches the definition of a pyramid. Now, real quick, this is cut out of, if I would have done this, I would have actually made a better pyramid than up here, okay? If I would have done this in the first place, if I take every corner, do you see how a pyramid can be cut out of a rectangular solid? Look at that, that's really good, look at that. Gaze upon my horrible art, that's really good for me. Do you guys see how I can chisel out a pyramid from a rectangular solid? What's the formula for the volume of the rectangular solid? Length times width times height. The volume of a pyramid is always 1/3 the area of the base times the height. So in this case, it's 1/3 LWH. Isn't the area of the base L times W? All right, so what about a cone? Do you see how a cone is chopped out of a cylinder? I can chop a cone from a cylinder, yes? Does anyone know the formula for the volume of a cylinder? Erase my horrible little...
It's like pi r squared 1.
Good, it's a repeated circle. So it's a circle that's repeated this many times. It's got a height to it, it's got a radius to it, are you with me? So it's a circle that's been stacked up that many times, yes? So that's why it's the volume, that's how much space it goes through, yes? So the volume of the cone will be 1/3 that. 1/3 the area of the base times the height. So the cone is the most basic pyramid. Okay, maybe. I just want to show you this. I'm not going to make you memorize this, okay? I'll give you the formula, but it's kind of nice. Sorry. So coming back to this dude. Do I give it to you in the back? No, I'm evil. It's too bad for everybody. Okay, so now I just gave it to you. Water is draining at a rate of 48 pi cubic feet per second from a conical tank with a radius at the top of 20 feet and height 60 feet. So if you draw this bad boy with the pen that's turned on, radius is, where'd it go? 20 feet, and the height is 60 feet.
Okay.
Draw and label the cone, choosing an arbitrary height of water. So at some arbitrary time, the water is going to be at some height in the cone. So it doesn't matter where I put it. I'm just going to pick somewhere in the middle just to put the top of my water so it's draining out over time. So maybe there's a hole at the bottom. Maybe at the very bottom, somebody, like I do, eat my ice cream. At some point, you bite the bottom off and you suck the ice cream out of it. Just make everybody around you feel uncomfortable. So if I put the water here, what's this?
That is 60 minus x? No?
Don't overthink it.
Okay.
H.
H.
Oh. Yeah. And this, by the way, I mean, I made it choppy because of poor little water, but, right, what is this? R. So, I mean, wherever the water is, it's going to make its own. There's a perfect cone of water, correct? Because it exists inside of this cone. Just like cats, water takes on the shape of whatever it's in. So cats are by definition liquid. Is everybody cool with this picture? You guys see that? Do you guys see right triangles in there?
Yeah.
If I do what? If I draw in center line, which will actually be another place I could have put the height, correct? So this is 60 feet. This is H. This whole thing is 60 feet, yes? So I see similar triangles. I see a small triangle, that's H and R, and I see a big triangle that is 60 and 20. And that one lives in that one. Therefore, the angle they have at the base is different. Can't be different because one is inside the other one. Shit. So they share the same angle. So what must be true then about the side lengths? You can set up any kind of proportion. So the one I normally like to do is like little side to little side equals big side to big side. So you could do, doesn't really matter. You could do little r to little h equals big R to big H. Whatever proportion you set up will be equivalent to any other correct proportion you set up. You could do R to 20 is H to 60. That's equivalent to what I just did. Okay. So I've done that a little early, but it's okay because the prompt didn't ask me to do that, but we sort of got ready for it. Let me do it over here so I can reference this easier. Some people didn't come today just so I can have some more paper. I appreciate that. That's what I'm going to assume. Find an expression for the volume of water in the tank. So what's the volume of water in this tank? And I'm not looking for a number because there ain't no way you're going to give me a freaking number, because what's the height of the water in the tank? H. What's the radius of the water in the tank? Okay, so what's the, what did I just say earlier? What, did somebody remember the volume formula for a cone of water? 1/3 pi r squared H. I love it. Do you guys notice there's more variables than we're used to in there? Do you wish there was a way to get rid of some of them? Maybe get rid of one of them, so then I'll only have two left, which is what we're used to having, y equals 3x, two variables, right? Do we have a relationship between, for part C, did we already kind of do that work? Which one do you want to replace? Let me see, well, let's look ahead a little bit. So let me put this here. Here is the relationship. How do I tell, of course you can reduce this. I can get rid of one of the variables if I solve that for the other one.
Yeah.
Or solve that for that. So what I, let me see, what this is a little bit evil. Okay, here we go. I wasn't as evil as I thought. In terms of radius alone, I do say that. So if you have a problem like this, you have to choose which letter to let go. I'm just telling you to write in terms of radius. So I'm telling you to get rid of H, correct? I'm telling you to get rid of H. In the problem, you would need to see the fact that they might give you dr dt, but they don't say a word about H, which tells you get rid of H. Do you guys see what I'm saying? So in a problem you're going to see, you need to see from the context of the problem which letters are important and which aren't. Which can I get rid of? When will that happen? When the function you're working with has more variables than you want. I want to be able to get rid of one of them. Say again?
R equals H.
Yeah, so I can take this, and I want to, which letter do I want to get rid of again? H. So I'm going to solve this for H. So H equals 3R. Is that cool? And here's why. You solve it for the letter you want to get rid of, because now you can replace H with 3R. So if I start with what I got, what can I replace H with?
3R.
And that's going to make my equation a function of radius only. Yes?
I'm kind of confused by
Are you cool with what we did earlier with the similar triangles?
Yeah.
Okay, so you're cool with this?
Yeah.
20 over 60 reduces to 1/3. And then if I cross multiply, you get 3R equals H. Right? 3R equals H.
Okay.
Cross multiply. Yeah. That's the one place you're allowed to directly cross multiply is when you have fraction equals fraction. A lot of people try to do it too often. That's the one time you're allowed to do it directly. So do I have, if I solve this a little bit, the 3's cancel, yes? So then I get volume as pi r cubed, and that looks much better. I don't have to use product rule, for example, now. Do you guys see it? The original way it's written? Wouldn't I have to use product rule if I tried to do derivatives? Do you want to? No, screw that shit. I know more information. I can use what I know to make this better. And again, what do you always do before you try to throw calculus at a problem? Simplify it. So I had more information, I simplified it. Now I can throw calculus at this thing. Sorry, such a weird way to say it. So fire, throw calculus. So at what rate is the radius shrinking when the radius is 16 feet? And by the way, what did I say at the very beginning of the problem that I haven't written down? So what is this in symbols?
dv over d, no, dr over dt.
Careful. It's cubic.
dv.
dv dt.
dt.
Yes. dv dt is 48 pi cubic feet per second. Did I remember that right? Yes, okay. Okay, I like it. I was very precise with where I put this valve. So I know that, and this is telling me radius, so I want to know dr dt, that's what I want to know. So how do I proceed from here?
So 48 pi equals 3 pi r
I see, so dv dt equals
3 pi r squared
3 pi r squared.
times dr dt.
Good. Let me make sure everybody's with us.
Yeah.
This is stuff cubed. I'm taking the derivative with respect to time. So how do you do something cubed? 3 times something squared times derivative of something.
Why is it dv dt 48 pi?
It is. So now I'm going to put 48 pi.
But I went from a cube to a square. Is that what you?
No, it didn't. What do you mean?
Oh, no.
Well, because I took a derivative, right? So
I
the
got
3
it.
came down, we pass it around, and then that goes down to 2.
Just trying to.
I'm with you.
So just try and write what you said there.
Yeah, trying to write it well.
Alright, I'm caught up.
All right.
Is that an S under feet cubed? 48 TI feet?
Per second.
Feet, feet,
Per second.
cube. Over second.
Yeah, 48 pi feet cubed per second. So now I can do like you guys are trying to make me. 48 pi equals 3 pi times what?
16.
16.
2 utes. What? And then dr dt. And then I just, so you almost always going to get to a point like this, where you just solve for the thing you've identified you want to know. Yes?
Do you need a negative for this one?
Oh, yeah.
Just shrink.
Yeah, you do.
That's classic.
So focused on making everything else make sense. So the volume is getting smaller over time, yeah? So it should be negative. And it should make sense if water's draining out, then the radius should be getting smaller as it approaches the bottom of the tank. hopefully it makes sense. I mean, I'd probably give you a picture, but most people would not put a conical tank like that. It just comes out. That's not a good way to do your conical tanks, kids. Let's see, 3 times 16 is 48. Pi goes away, so it's 16. So it's negative 1/16, so it's negative 0.067, I think. Negative point. I don't know anymore. 0.625. Yes. Is that what you guys got? Anybody do that? 0.625?
0.0625 maybe.
Yeah. Who's the Watsons? Units, I'm sorry. That's what that is. Yeah. What was it? Feet per second. So that's how much the radius is changing. Now, I want to show you a nifty little trick on part F. Do we know how quickly the radius is changing? When the radius is 16 feet, do we know how quickly? Yes, right there, yes? Yes? Do we know how the height and the radius are related? Do we have a relationship between height and radius?
Yeah.
Yes.
3R.
Yeah.
Height is 3r, yes? So don't they want me to know the dHdt? Isn't that what they're asking me for? So don't redo the whole damn problem. I know how quickly the radius is changing. I have a relationship between h and r, so I can set up a relationship between the rates of change. So if I take a derivative of both sides, I get dHdt equals 3 dr dt. Is that cool? Just take a derivative on both sides, respect to time. So the dHdt is 3 times negative 0.0625. My 6 went away. Oh my God. Which is negative 0.1875. Feet per second. Bless you. So you don't have to redo the whole problem and solve for h instead of r and all this kind of shit. You already have a relationship between h and r. Okay, I'm sorry, I'll put it back. So, there will be problems that don't fall into one of these 3 formats in section 3.9. But they all have the same idea. Draw a picture, find your variables, symbols for what they tell you, symbols for what they ask you, derivative. Plug shit in, yes.
You know the homework, it talks about like all this and then the guy's moving away from it at this rate. Is that triangles?
Could be triangles. There's one like a shadow or something.
Yeah, like a shadow.
That's very often a triangle because you have a lamppost, you have
Yeah.
a person and a shadow. That's a triangle. Yes.
Okay.
Yeah.
I see the answer. But
That one's a little tricky because it's like how quickly is the tip of the shadow doing something.
Yeah.
Yeah. That one's gonna be neat. You guys are funny. Some of you guys think we're done. Yes.
For
Right.
part F, did we?
Oh.
We have done it like we have done it without knowing the relationship between R and.
No. No. Because we couldn't have gotten drdt without knowing this.
Yeah.
I need you to understand. I could have done a product rule here, correct? But then I would have had to have known DHD. I would have had to have known, and I could have gotten it from this. It would have just been a lot more work. I could have solved this for R and put that in here and gotten a volume function as a function of H. And I could have done all the same shit and gotten dHdt the same way we got drdt. But this is just a shortcut. I know the relationship directly between H and R. Yeah. So whatever the change of R is, height's got to be 3 times that, because the height's always 3 times the radius. All right. Let me see if you guys can handle this. Do I want to do this right now? Yes. So on this problem right here, no, I'm not going to do it right now. We'll do it next. What I want to do right now is I want to step into the next section a little bit. Low battery. much battery? 10%, I'm good. You guys are all like, come on, battery. Die, battery, die. Yes?
Can I get your worksheet like for,
What? Oh. This guy. Sure. No. So you guys, help me out. What are the equations of a line? Was it the wrong one?
Yeah.
Y equals mx plus b,
Okay, y equals mx plus b.
or y is
I get it started.
y minus y equals x minus. Oh no,
MX minus x.
Now,
x minus.
go with me for a second, okay? If I give you a function, and I want you to find the equation of the tangent line for this function at x equal 2, what would you do? Take the derivative, and what would that be going towards? Getting the slope. Let me call this a, just on the side, because couldn't that be different? X equals 2, x equals 3, x equals a, just whatever, right? So how do I find the slope? I would do f prime of a, correct? So what's f prime of a? In this case, it's f prime of 2, which is 16. That's the slope. What else do we need? Point. So how do I find the point? Yeah, I know 2. So then I plug it in to f, correct? So I get 2.
216.
You guys with me? And the way I do these is I do, well, let's do it all the way out, Jeff, because you're doing something. Y minus y1 equals m times x minus x1. Okay, so, right? We've done a ton of these. You guys agree? This is one of the problems we've done the most of. Could be because it's very important. I don't know. So let me write this in symbols. I could distribute the 16 and all that shit. We've done that. Let's do something freakier. Where did the 16 come from? Wasn't that f evaluated at what I called a? Is that cool? Wasn't that f of 2? Is that where we got 16 from? Where did we get this 16 from? It's a bad choice of function. Give me a break. Sorry. That was f prime of a, correct? And then this would have been x minus the a that I picked. In this case, I picked 2, so it was just whatever number I wanted to pick. Are you guys with me? Is that different? That's the stupid tangent line, correct? And you're all like, well, if you want to call it stupid, Jeff, I agree with you. The point I'm trying to make, what really sucks about section 310 is it makes it seem as if it's entirely new. No, I wish they titled 310 tangent lines. What the shit do we do with them? Because have we done anything with them? Have you found them? Oh, hell yeah. Have you done shit with them? No. I have no idea. You guys are like, I really didn't think about it because I was just happy it was done. And now you're telling me there's a part B. No. Too bad. There is. So here's what a tangent line is all about. So let me do this. I'm going to do something that should make sense. Are you? Yes. All right, what was it? It was y equals f of x equals 4x squared. Okay, and the point was 2, right? So that would be 216. Good job, John. If I zoom in on the point 216, it doesn't take much zooming. If you came in and I had this on the screen, would you tell me this looks like a line? Of course you would. Any well-behaved function, any differentiable function over some interval, if you zoom in enough on it, it will look flat. Which is why there are flat earthers still in existence. And if any of you are, don't tell me, just I appreciate you in the right place. People think we're in the flat earth. Yay. Because locally, we're so close to the damn curve, it looks like it's a straight line. Now we know that's a freaking parabola because you saw me, you can see the freaking equation still there. You know it's a parabola, but it looks freaking straight as shit, yes? If I graph the tangent line, isn't it gonna hug this line pretty well for a little while? Yeah. So I could use the tangent line to estimate outputs for this function if I use it close to 2. So let me graph the tangent line. What did we get again? I forgot. We got, shit, you went to sleep because you're in low power mode. Here it is. We got y equals 16x minus 16. If you solve. No, Jeff. We'll zoom out a little bit.
Jeff, when you say close to 2, are you thinking of like almost a limit? Like after the
Yeah, sort of. Do you see if I get far away from 2? Like if I go here, is it close? Is that blue line close to the red line? No. But if I get closer to the input of 2, do you agree as I get close? Now real quick, here's my 2, yes? Everybody see the 2?
Yeah.
So this line is 2. As I get closer to where 2 hits my red line, aren't the red-blue line almost indistinguishable from this height? Now if I zoom in, I'll see the difference, but I gotta zoom in a lot. Yes? So if I use the blue line to estimate the red line's outputs, it's pretty good as long as I input things close to 2. Do you guys get the idea here? So this is what's called local linearization. If I have a differentiable function, anywhere I pick locally, it looks like a straight line. If I don't stay local, now it's very obvious that straight line is not straight. It's doing all this curvy shit. But if I stay really close, it looks freaking straight as shit. You guys kind of with me? So what good is this, Jeff? Good question. That's what I would be asking if I was one of you. Shit. Wake up. Damn it. I forgot to plug you in. I'm so sorry, little dude. So let's pick a funkier function. Square root of x. They're going to say, find the linear approximation for square root of x around x equal to 1, let's say. You interpret that to say, find the equation of the tangent line at x equal 1, because that's all it frickin' is. So let me show you. I should have made this point over here. They're going to say the linearization of a function is equal to f of a plus f prime of a times x minus a. Do you notice how if you just add this stupid thing over, you get that? I need you to see that. So if you're not careful, you will go into section 310 thinking it's all new, which is not true. It's just finding the equation line. We're now just going to finally do something with the damn thing. We're going to approximate answers to the original function. Do you all agree that taking the square root of something is not easy? If you don't agree with me, what's the square root of 1.2? Thank you. Okay, so I want somebody to go. Watch it.
Greater than 1 plus 2.
Huh?
Greater than 1 plus 2.
Oh my God, he did it. Okay. So all I do when you see a problem, you say find the linearization or find a linear approximation of this. Just say to yourself, tangent line. You've done that a lot. Nothing new. So how do I rewrite this, of course, considering Jeff's rants about shit?
X to the 1/2.
Yes. Thankfully, my rants still have a point. Right? The day they don't have a point, tell me to stop. Retire. Yeah, I hear you. You're like, sorry, there, Mitchell. So I take a derivative, of course. Then I want to plug in 1. You all agree that would be 1/2? Is that cool? All right, let me stop for a minute. You guys all take the derivative, plug the x value in to get the slope at the point I want. What's the point that we're working with?
1, comma.
1 comma 1.
Would become 1 half the negative 1?
Say again? Yeah, 1/2 times 1 to the negative 1/2. What's 1 to any power? 1. So then 1/2 times 1. Okay. so that I get y equals, let me see if you guys are cool with this. You agree with me that it would start off as 1/2 x? If I put a 1 in, I'm supposed to get a 1 out. Do I currently get a 1 out? How much do I have to add to make it become 1? Okay, that's the ultimate best way to get freaking mx plus b. Yes? Now that's a relatively easy example, but still. Okay. So still, Jeff, what good is this shit? If you plug in anything close to 1, I can get a reasonable approximation for it by using this instead of the square root. So let's look at 1.2. What if x is 1.2? What's our approximation then going to be? 1/2 of 1.2 plus 0.5. We just write it as a decimal. What's 1/2 of 1.2? 0.6. What's 0.6 plus 0.5? 1.1. Can somebody please do the square root of 1.2 on your calculator? Calculator.
1.0954.
Doesn't that round to 1.1? Are we exactly right? Are we pretty good for government work? Yes. Okay. Of course, I would for the government. But
Government's pretty strict.
They are. They want it.
They want you to believe the earth is round.
that would be useful. That would help. That would make me feel less sad. Okay. So that is, we're finally seeing, we keep talking about how to find these damn tangent lines. And I have no idea if this makes anybody feel any better, but we can use this shit for something. So when we have some situation where we don't have to be exact, if I'm writing a computer program and I just need to get approximations, I can use this. It's less computing power. I can have some, do you understand? As long as I can take the derivative, it doesn't matter how ugly the function starts off as, I can make it become locally linear. I can find mx plus b. That will work close to the number I built it around. Are you guys kind of with me? Wouldn't this equation have been different if this had been different?
No.
So I must use the right thing around the number that I want to be close to. So that's why I picked 1.2, because it's relatively close to 1. If I put 3.8 in, am I going to get a decent approximation? Probably not. I'm getting pretty far away from 1 now. I'd rather build it around 4 then, yes? And it has its own equation. Are you guys all with me?
Like you were saying, like limits, because you're close, so.
Yes, which is making me sad that we skipped 2.4, because 2.4 actually defined close with epsilon and delta, and it doesn't matter. So some of you guys, I think, did the extra credit. I think I made it extra credit. I don't blame you if you didn't do it. You're like, dude. All right. But that kind of taught to formalize the idea of close. Okay. So all 310 is, if you read the section, you will see this formula, and it will feel as if it's new. And it's just frickin' y plus m times x minus x1. y1 plus m times x minus x1. It's the same stupid formula. So just find the tangent line, and you can use it. I think I'm going to make everyone very happy. I am going to talk a little bit about 311. 311 is, and you're like, this is not making me happy, Jeff. Hyperbolic trig functions. I am going to make this extra credit. I almost didn't because of that reaction, but I figured do it another way. Extra credit, right? E comes before D too many times, so credit. Extra credit. But I will talk about it a little bit next time. I'm going to let this out a smidge early, like I said I would. Yes. Oh. This has to be input to the original formula to figure out what the output is. Square root of 1 is 1. If I put it in here, I'll just slow it. Yes. Willis. Did anybody else not get their test back? Coming up here if you didn't get your test back. Everybody.
Isn't 82 slow?
Can I do get bonus points for credit if I didn't?
Not for credit. I mean, I can tell you if you got it right, but you get one shot at bonus. Yep.
Thank you.